Hi there, I'm Peter, Managing Director of GlasCurtain, and today we're back for episode 8 of Curtain Wall Conversations. And today we have the privilege of chatting with James Satterwhite of Advanced Glazings Limited, North America's leading manufacturer of engineered light diffusers for daylighting. As the Chief Executive Officer since 2014 and Vice President of Global Business Development since 2015, James has had a huge impact in helping architects, designers, and clients maximize the human experience of daylight while effectively managing thermal values. Working with some of the top design professionals in North America, James has ensured that hundreds of successful projects have improved the quality of life for occupants and the environment. We're proud to say that one of those projects we worked on together, actually, which was the Nunavut Arctic College in Iqaluit in far northern Canada in the territories, designed by Teeple and Sibonell. So in today's conversation, we'll delve into the evolution of the glazing and facade industries, the environmental impact of manufacturing and building construction, the technical nuances of his company's Solera products, regulatory challenges in the glazing industry, and the opportunities we both see for brighter days ahead at the intersections of innovation and sustainability. James, thanks very much for joining us today.
Thanks for having me, Peter. Glad to be here.
Wonderful. Well, let's kick things off. I mean, you've been in the industry for a couple of years now. So in your time in this industry, how much has glazing and facade performance changed? I mean, it looks like we're on the cusp of a whole bunch of new changes, but where have we been? How did we get here?
Well, you're asking me to date myself, so I'll start off by thanking you for that, Peter. But yes, I've been around for a minute, as they say in today's world. But it's interesting because my career has been developed all along in putting things on the outsides of buildings that bring in light and all kinds of different materials of construction and the like over several decades in the industry. And things have definitely evolved a lot. But if you take it down to the very nuanced beginnings of glass, because that's what we're really talking about here today, is, glass has been around for centuries actually now in terms of what it is and what it does. But the way to make it has evolved, the quality of the finished product has evolved, and the cost and industrial scale have evolved over time. But that has to do with the evolution of glass itself. But glass itself was what was first put on buildings many years ago. Single panes of glass in very small pieces in complex constructs to be able to put openings on buildings. And over time, things evolved in different means of manufacturing. It came from what used to be drawing glass and casting glass to the origins of float glass, which was a different way of making it, which really helped to bring it into extremely good clarity, but also extremely large supply infrastructure to bring very large quantities of it to market at effective cost and effective pricing. And the infrastructure in the general industry was built around supporting that. And that's at the very heart of the glass industry today. Float glass manufacturing with the evolution of various tinting options, various different tempering and laminating options, and then evolving into coatings that could go on the glass, which very much get at particularly managing solar heat gain, but with minor incremental changes in thermal value of the assembly of glass. But glass started as single pane. People needed better insulation, so 2 times 1 is better than 1, and that's where the industry went to double pane glass. And then these other innovations came in, and the markets have evolved, the consciousness in the industry is involved, and the environment has evolved, and constantly pushing for higher and higher performance of glazing on buildings. And at the same time, there was an industry charged motivation towards getting embedded into the design community and the expectation on the design community that maximum visible light transmittance was the key to a good piece of glass, and maximizing VLT, and to some extent they're harnessing themselves into a problem where heat gain was becoming a bigger and bigger issue. And that comes completely attached to visible light transmittance. Thereby, that's where low E coatings came in, because they could manipulate the solar heat gain, the infrared transmission, to a level which didn't impinge terribly on visible light transmittance. But the trade-off between the two was in really small incremental differences. Insulation requirements needed to change, so the industry moved into double pane. Now it's in triple pane. There's even some crazy quadruple pane, multiple buildup things that are going on. But in all cases, they're incremental modifications to the normal process for making it, because the infrastructure of the industry is very rooted and very mature. And it's a very large industrial base that is used to make glass that goes on buildings. That they're very automated, very highly automated lines of production that are set up to handle very specific unit operations through the evolution of glass as it moves from raw material into finish. And making things different in that industrial infrastructure is hard to do. So making more out of more of the same thing is really what the industry has done. And that has brought the industry kind of to where it is today, where they're really kind of fighting that, because the industry has not been able to keep up with the requirements of the global environment we're in, the mandates, the sustainability culture, all the rest of those things. So it's evolved a lot, but it's really kind of up against the wall right now.
And do you see much difference in some of that adaptability in different manufacturers or from different areas of the world? I mean, it seems like, Europeans are doing one thing and the Asians are doing another and North Americans are doing it. Do you see much difference, or is there a whole bunch of similarity because everyone's kind of using the same core industrial processes?
Yeah, it's a really good question, because they are generally all bounded by the same problem, because the process to make it is what it is. And as long as you're relying on the same thing to do a different set of things, you've got kind of a division in how things work. Europeans have had a macro environment in their markets that have forced them to make further adaptation and customization to how materials go together to improve thermal performance, much more so than here. And China is actually behind that whole wave, and they're developing a big infrastructure to feed an existing market, not necessarily an innovation platform there. So most innovations that you see are going to come out of Europe. And slowly, the North American markets typically trail the European markets by not necessarily a decade, but by some subset of the decade to bring it to market. So yeah, that's probably a good answer for you on that global scale.
And in your time in the industry, have you seen more of the sort of drive for innovation coming from, I guess, sort of architects or manufacturing leaders, or is it coming up from the code? Like, is it the ceiling that's getting pushed up and dragging up the floor, or is it the floor that's pushing up and pushing that space towards the ceiling?
It's definitely not from the floor up. The demand is coming from owners to a certain degree, but more importantly to mandates for carbon reduction that are being mandated at a very high level, which is forcing people into thinking about changes in thermal conductivity with these facades on buildings and the balance. So the industry is coming along, but they're coming up, but they move really slowly.
Speaking of innovation, where does Aerogel fit in? I know you have experience with this aerogel. It sounds very space agey. I know that your company uses it. It sounds really exotic and cool to us. But where does this material come from, and why is it useful or important for this day and age?
The cool thing about aerogel is it's not new. It was invented in 1930, a long time ago, by a scientist who was researching on find ways to manipulate what happens with thermal conductivity at very nanoscales. And they developed a process to make a silica-based material that would go through a gelation step, which was taking silica and some other things together, putting it through a hydrogelling process, and developing this very, very porous makeup of silica. And everywhere where there wasn't silica, there was liquid based. And the theory that he had is we could grow this complex network of silica strands at a small enough porosity scale, and then be able to figure out how to get the liquid out of that without losing the structure of that aerogel. We should end up with a really interesting insulation material with really interesting insulation properties. And he actually did perfect at a lab scale being able to do that. And it quickly became known as the world's highest insulating material and the only insulating solid material in the world that could insulate the way it did. When you're thinking about thermal conductivity, there's three different things that are in play with it. There's conduction, which your product works a lot on that conductive disconnect in the entire assembly. There's convection, which is movement of air. And then there's gas phase conduction. Convection it's a problem for everybody, and it has to do with how air can actually make heat move. Gas phase conduction is how air molecules can actually pick up radiant energy and excite themselves and then move the energy across those molecules by touching each other as they get agitated by this temperature differential. And that gas phase conduction was the weak link of everything out there. And any super insulating materials that you see in the world have solved for, at minimum, convection, but at best, convection and gas phase conduction. And that's what aerogel does. The pore structure of aerogel is, we get into too much physics here, but there is a distance in static air between the air molecules. It's known as the mean free path between the aerogel molecules. And as long as the temperature gradient across a bed of air or an area of air is static, the air molecules don't even interact with each other. They stay apart from each other. But as soon as you excite one area of that with a different thermal property, the molecules in the presence of that start to get excited and they start moving around and they break that mean free path. And that mean free path in static is about 20 nanometers in size. If they stay apart, you have no gas phase conduction. As soon as they start moving together, they start touching each other, and that's where they pass the energy between them. That's the weak link. And that's what aerogels solve for that no other material has been able to, because the pore structure in the aerogel, and it's an open pore material, is smaller than the mean free path. They're about 10 nanometers, 10 to 20 nanometers in size. So they're actually smaller than that mean free path. So they get in the way of the molecules being able to interact with each other. So you get a temperature gradient across, but the air molecules can't touch each other. That's what makes it insulate, and that's why it insulates so much better than, it's actually the highest insulating material available in the world. Another nice thing for the industries that you and I are in the particular means of the aerogel that we use, which is at an industrial scale, it happens to be almost water clear. So it's very highly light transmissive. So if you can figure out how to put it in light transmissive materials, you're getting the benefit of maximizing daylight benefits as well as reducing thermal conductivity of the materials, which is a big boon for this day and age for thermal envelope.
And so do you guys use aerogel in all of your products, or just sort of like flagship products? Or
we use it in actually the majority of our product. We have some products that don't use aerogel, but we use varying amounts of it to achieve different thermal conductivities. We have materials that will insulate at the low end at an R3 scale and at a high end up to R25, which all have really significant light transmission available for them as well. So you don't need one particular thermal conductivity. One doesn't need to suit all kinds of applications. And we do projects with a wide range of different types of buildings and different structures. Different geographical locations will change what their thermal requirements are. So we have a real wide range.
We are one of the few, if only, leveraging fiberglass framing, obviously up here. Are you guys one of the only ones leveraging Aerogel Tech?
The commercial environment for making aerogel is still reasonably new in the scale of evolution, but the supply chain isn't that large. There are several manufacturers that make a blanket form of the material, which is opaque. It's made completely differently. It's using very critical process drying to get liquid extracted from it. It's very opaque. It's made for and is used for in industrial insulation applications, specifically in the energy sector, in high temperature energy structure, in cryogenics, those types of things. Very industrial, opaque, not very attractive material. The material that we use is made in a different process that is not a blanket form. It's actually made in a granular form, which suits our manufacturing process. And it also is not opaque. It's this very water clear material. Both those materials have similar thermal conductivity, just different forms. And we use this granular form, and we have actually the perfect environment to make it work in this industry, because we make glazing materials that are anywhere from 1 inch overall thickness up to a 4-inch overall thickness. And when you get into the thicker glazing units that we make, and those are all relative to different insulation performances. If again, we keep getting into too much science, but I have to at least explain it. When you get a 1/2 inch airspace between two pieces of glass, you will not develop condensation in that space. The Rayleigh principle will not allow that to happen. So you don't have convection in play there. You have radiant energy, you have electromagnetic radiation, and you have gas phase conduction going on in that space. That's where a typical IGU will only develop so much insulation performance. You would think that if you went to a thicker interior air cavity, you would get better insulation, but actually it's diminishing returns because now you're all of a sudden introducing convection to play, and you have gas phase conduction. And so you've got this cascading series of problems.
Don't tell that to the Europeans, because the European modeling software, and we had another podcast on this, when you use a 0 degree sort of lower bound in your modeling software instead of -18 Celsius, it actually privileges a larger airspace. So you end up with a 3/4 inch airspace in North America, when we model it to -18, we'd use a 1/2 inch airspace. So, your assumptions about the world very much dictate, that convective potential.
Absolutely. And different people will look at it differently. But same things are happening. The physics of that are in play. So when we make the thicker units, we also create a honeycomb material that goes into that space it's basically a woven together PMMA honeycomb material that's very highly light transmissive. With about 8 millimeter flutes of open space in between them. That serves one function, which is in the region that it was originally invented, was to deal with the convection. Because you put that into those thicker spaces, you eliminate convection from being able to happen. You do get a significant boost in the thermal capability of that thicker IGU. It also is a perfect place to house this aerogel within those flutes that are in it, because the granular aerogel needs to be stabilized in an environment that keeps it where it was when you put it in there. And that's really the reason why our product is so unique. No one else is doing that, and there's no one that we can see on the horizon that is doing that in any degree. And so for right now, knock on wood, we have a good position, and the demand for the product is growing substantially because of this environment that we're in. There are aerogel initiatives going on with small scale companies. It's good to note this. The holy grail for the glass industry with aerogel has been to always create a water clear aerogel, which means you have to make it in a monolith. It has to be in a solid form. And that is difficult to do at size and at scale. And also the weakness with that is that these monoliths, especially the good ones, and I've seen a number of really good ones. I'm here in the Boston area. There's a number of initiatives going on at MIT and a few other areas where they're getting some very impressive results. But the monoliths, the other weakness to them is that they're also incredibly friable. They're very, very delicate. So putting them into a construction material, putting it under wind load or impact and things like that, isn't necessarily intuitive. There's some interesting things going on, but they're all still lab scale. Some are maybe a little bit above lab scale, but they're a long ways away from being commercialized. But that's where the industry is heading. The clear glass industry is, I think, we're going to get into this a little bit later, but there's a few other innovations in the clear glass side, and there are some aerogel things that could actually impact it as well. But the materials that we make are not clear vision. They are translucent. They are light transmissive vehicles, and they are almost always used in conjunction with clear glass and vision glass to create really interesting effects on both insulation as well as interior illumination.
With fiberglass, one of the technical hurdles that we've had to overcome, and we have now, is combustibility for non-combustible building envelopes for flame spread ratings. That's one thing where the code, even though aluminum and fiberglass are both technically combustible, we had to pass additional testing, which was fine. We did that, no problem. But is there anything like that with aerogel, or is it just ready to go from a regulatory perspective?
No, there's combustibility is not an issue with these aerogel materials. Well, I should say that not wholesale. There's two primary forms of aerogel. One's a silicon process, another is a polymer process. The polymer process is actually being developed for other things, and their combustibility is not known at that area. But if it's silica-based, it's non-combustible. It's the same thing glass is made out of. So combustibility is not an issue. The hurdle is purely technical to begin with. When you try to create aerogel under a supercritical process, there's as I said earlier, you've got this fluid of silica particles and liquid together that you put through this chemical reaction that creates this silica structure, if you will. It's like a sponge. It has all the liquid inside of it. And you've got to get that liquid out, like I said, without losing the volume. To make the monoliths and to make the water clear, you have to use a supercritical process, which means you're size specifically related to taking and creating that, and you have to put it into supercritical pressure and temperature to dry the liquid out while holding the volume of the mass of silica sponge, if you will. The materials that we use scale easier because they don't use that supercritical process. They're dried at ambient pressure and temperature because of a chemical reaction that's caused inside of in the chemistry of it that allows for the pores in the drying process to collapse while they're drying, but they don't want to touch each other, so they will stay away from each other, so they will spring back once they've reached the dry state and achieve that porosity. The difficulty for these other innovations is overcoming that supercritical process and scaling that into levels that are useful, especially as the world is going into larger and larger pieces of glass. They're kind of chasing the back end of this trend, because you know and I know jumbo is it, or as close as we can get to jumbo is it, because it overcomes some of the other problems that the industry is trying to salvage themselves away from.
It doesn't sound like there are huge regulatory hurdles. It sounds like there are some definitely technical, industrial kind of hurdles. Are there objections or hurdles in terms of adoption with architects and designers? Why wouldn't an architect or designer want to use these high performance solutions more?
Well, it's funny because I said this earlier when we were talking. There's one caveat to what we make is you can't see through it. These are translucent materials, and if there is an objection to that, it is this architectural community's ubiquitous use of large expanses of clear glass, and which is okay. It's a style and it's a process, so that does create objection. So that makes our job, I would say, more entertaining and more difficult to convince them as to why vision isn't everything that it's cracked up to be, because of the bad things that come along with just using large expanses of vision glass, which are, there's many of them, but most often it's all kinds of remediation materials that have to be added to solve for the weaknesses of using tons of clear glass, which is window shades, all kinds of room darkening effects, which really kind of go against why putting all the glass on. So that's probably the single limiting factor that we've had, is because you can't see through it. But the way that the codes have come to this point is it actually works to our benefit, because the way we can insulate to these high levels and integrate directly into curtain wall along with clear glass, very much so in your curtain wall, get some amazing insulation levels to the overall assembly compared to the norm. And we can keep the illumination levels up in the spaces that people are meeting the mandated illumination areas, is a big benefit, because if they didn't have those materials to meet these codes, they're using less clear glass because they have to, and they're using more opaque materials, which goes away from the daylighting benefits. And we can solve both of those things in one pass, and we can keep one curtain wall doing all of that work. And quite frankly, do it probably less expensively than going to all those other perturbations.
Right. Yeah. No, it's funny to think, as premium products, what does premium mean in the context, right? It's like, yes, well, if you look at one little tiny light item, maybe it's a little bit more expensive. But when you think of the context, okay, well, now we're adding blinds. Now we need more artificial lighting. Now we need more mechanical. Now we need da 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 da. It's like, well, wait a minute. Maybe this is actually, we end up way ahead if we look past this one line item and look at, I don't know, 2 line items, 3 line items, 4 line items, like, not, we don't have to zoom out to 1,000,000 feet, but, even looking at 2 or 3 line items, it can make a big difference.
Yeah, you have to position it at total cost of ownership. If it's purely an overly simplified first cost calculus, anything that is a quote unquote premium product is more expensive. Or is it, and I'll just use this quite frankly, or is it that other materials are just cheaper and less expensive? Does that necessarily make them more valuable or less valuable? Depends on really what your overall objectives are. So I don't find any reason to say that the way that we put this is we start with an IGU like everybody else makes, the commodity IGUs, which are all great and they're all really well made and all the rest of that. But we do things to them that add lots of value to them. So at what level does that value demarcate from what's needed on a project? That's why we have multiple levels of insulation performance and all the rest of that. But if you've got a high performance envelope, like the things that you and I are working on, and the high performance is a really high requirement, it's very difficult to de-emphasize the value of what it is that you're bringing.
In terms of some of that, sort of holistic thinking, we're obviously hearing more and more conversations about carbon, like you mentioned. And as we sort of get better and better at the operational side, we're also now looking, of course, at the embodied side. Where do you see those conversations heading? How do you sort of cater to those kind of viewpoints, and how do you emphasize that in your sort of marketing or product manufacturing for that matter?
Well, we're challenged, like everybody in this industry is, with keeping up with the EPD requirements and all the rest of those things, which are ballooning out there. And we are underway with developing our EPD now, as well as our aerogel manufacturer is doing that behind us. Also, we are intuitively and at a surface level understanding that we should perform very well. We perform extremely well from an operational standpoint. That's a real simple case to make. But the embodied carbon elements and the total manufactured and end of life cycles that we have to get through, we're not sophisticated to the level that we've got that nailed down, and we've got a team working on that now. I think you've solved that. You have your EPD on your product as well, right?
We actually have our LCA, life cycle assessment. The LCA tells you much of the same information that an EPD would. EPD goes a little bit further, but EPD also makes other kinds of assumptions. But yes, we've had our life cycle assessment for a number of years now, and it shows 60% reduction relative to aluminum. So that's our benchmark in our space. And of course, even if it was 0%, embodied reduction, we'd still have, again, that a huge operational benefit. We're basically doubling the thermal performance of the facade. So, it's important, and we see more emphasis in the conversations. But yeah, absolutely, thermal performance is definitely number one.
Yeah, and it's operational carbon, but we supply our operational carbon benefits from several different sources. One is obviously thermal performance, but also illumination can do a ton to support reduced operational carbon. If you can get better illumination, deeper into spaces, reduce zonality of mechanical systems having to be balanced for bright zones, dark zones, plus you're using more completely carbon-free light, which is sunlight. There's no embodied carbon in that at all. So you're using it more ubiquitously. It's a very easy equation to say this makes sense to do it if you can do it correctly. And having engineered light diffusing materials like we make allow you to much more efficiently use the available illumination of what's coming through glass. So the operational side it's a very strong case. The embodied side, I don't think we'll have as big of an advantage as you have, just because our comparative materials that would be used are similar to what we make. You've got something which is your pultruded fiberglass versus aluminum. Huge difference in terms of energy consumed, all the rest of that, in making those two different materials. Therefore, that's why time is now. So.
The highlight conversation in the space is ever evolved, right? For a while it's like you said, VLT is the thing to talk about, and then it's going to be thermal performance, and then now carbon is definitely du jour. What I think we're going to see in the next decade, especially as unfortunately the world is just getting crazier and crazier, is that being manufactured in North America. As you and I are also both our companies are manufacturing in Canada as well, is going to be more and more important in terms of supply chains, in terms of, reliability, in terms of tariffs and trade wars, and, all of these kinds of all of these kinds of, crazy things. So how is it? So you guys are, we're manufacturing in Alberta. You guys are manufacturing in Nova Scotia. How did, Sydney, Nova Scotia, for those who, wouldn't know where to even find it on a map, might not strike most of us as a big hub of innovation and manufacturing. So how did that happen? How did that come to be? And why is that a good place to do business?
Yeah, so it's a good question, and I smile when I hear you coming up and winding up on that one. But yes, for those of you in the audience who don't know where Sydney, Nova Scotia is, if anybody has flown up the East Coast, disembarking and going to Europe, you've flown over it. It's one of the last points of where you can go in North America. The reason that we were there is because of the founder. The founder was born and raised there. That's where his roots are, and I should say their roots because they're a married couple. But the founders did his postdoctorate degree work at Waterloo University in Toronto, and that's where he actually developed the concept for what is now Solera. He did his study in light and light transmission and human reaction to visible light, and he developed the concept for it there. And like most people that grew up in the Sydney, Cape Breton area, Nova Scotia, they always go back. It's amazing as we hire people at the business, they've either been there forever or they're coming back from other places to be there. It's a beautiful area. It's a lovely place to be. It's not the center of the manufacturing hub, but it is our home and it is where we'll stay, and we service our markets well from that location. As we grow, there will probably be some licensed fabrication in some other areas. We already export quite a bit of our material into the U.S. We have a foothold in Northern Europe as well. So as we grow, things will likely change, but the heart of our business and our R&D and our customer support center will remain there. I don't see any reason why that would change.
One other sort of area of innovation that I think you sort of alluded to that we might touch on at some point in our conversation is, new technology with regards to vacuum insulated glass. And vacuum insulated glass is another way to achieve ultra high thermal performance. But unfortunately, and so, basically for those who haven't, used or seen a sample of vacuum insulated glass, you basically start with, it's still triple glazing, at least the ones that we're using. But instead of having 1/2-inch air spaces, you actually reduce 2 of those air spaces to only about 1/4 of a millimeter apart. And then you put in little stainless steel pillars and suck out all the air out of it. So that you have a vacuum. And just like in outer space, vacuum does not conduct, vacuum does not conduct energy. And so the overall thermal performance of the glazed unit is about 50% better. It gets to about R15 is what we're seeing. Unfortunately, they're not made in North America yet. It sounds like there's some, companies in Michigan. I think there's one that's, starting to look at this. Vitro is importing the vacuum sandwiches from China and then at least hybridizing them in North America, but they're not actually making the vacuum here. So it sounds like there's some companies that are working on this. Where do you see, or how do you think about that technology? And is there a role for that to work with your systems? Does it need to be made in North America? How do you think about that kind of product?
So the vacuum insulated glass is it's kind of like aerogel. It's not new. It's been around for a long time. It was originally developed by Nippon Sheet Glass in Japan, and it's been there for a long time. You said it right. The idea is you evacuate the airspace in between. You get a super insulating material because you can't convect and you can't conduct in that kind of an environment. So it's a perfect environment. It does have difficulties with sealing the edges of the unit that are drastically different than making a standard IGU. And you do need to have these support pillars in the inside to brace the glass. The difficulty for commercializing that has been several. Number one is getting into large units greatly complicates the manufacturing process and puts at risk the edge seals quite a bit. That's been a big barrier for them for a long time. And as we know, in today's environment, bigger is better. The manufacturing infrastructure to make that has been very slow to come along. There have been several large efforts that have been put into them. Several of them have been abandoned because of the economics wouldn't work, some major producers. The effort with Vitro is a new thing. I don't know where that's going to go. And also the China producers, I think that you're using, as well as an unproven long-term process and material to go together. So I do think that vacuum insulated glass has a possibility, but it's a long ways away from being anywhere close to mainstream. I do think that in smaller sizes, which is I think where these US-based firms are actually focusing, there's some really interesting large-scale commercial markets for using that for retrofitting glass in residential buildings and residential applications. That's probably the low-hanging fruit, but also if they were able to actually perfect that, it's a massive market. Much bigger than any commercial market could actually be. So it's definitely there and it's coming. It's just a question of, it's like we've talked about that all through this conversation. What are the barriers to entry? What are the commercial? What are the industrial? What are the cost barriers and all the rest of that? Yeah, it's definitely there. There are a few other interesting innovations, suspending multiple films in between two pieces of glass to get very thick assemblies, which can get some pretty decent insulation performances, but they can't be glazed into standard systems. They need a whole completely different platform to be able to put them in, and there's just no scale. So you and I, with our combined systems, are kind of at the tip of the spear right now out here because we're commercially viable now. And not just new, we've been doing it for quite a while.
And we can scale.
And we can totally scale. That's right. And we're being tested with that right now. We're scaling quite a bit right now because the demand for the product is growing, and which is a great place to be. And it comes along with its other issues, but those are good problems.
These are all good problems to have, and we know how you feel, and good problems to have. What we're seeing in Massachusetts right now, where you're based. I mean, I'm going to be in Massachusetts very shortly. I mean, by the time this episode comes out, I'll probably have been home and back. But the Massachusetts market is really interesting to watch. How open-minded all the architects are suddenly having to become, and happy to do so, of course. But the code is pushing forward a kind of innovation and a kind of conversation, and that's I think playing very well to both of our strengths.
They're calling them the stretch codes here in the New England area. It actually goes all the way down into the Manhattan area in New York. They're very similar, but they're basically if you try to make it simple to understand, they're making passive house standards the norm. It's the standard for construction in terms of the performance requirements, which is a big stretch.
That's why they call it a stretch.
Yeah, that's why they call it a stretch. But that's the way that the buildings have been designed and constructed is not going to work. So there's new things that have to come into play. So yes, it's good for us, but I don't want to make that sound like it's opportunistic for us. We're happy to be able to help, but innovation such as what you've done and what we have done, if you innovate like we have in small companies, which is where innovation starts, you're typically got a long cycle to go from the beginning to where you're becoming really a substantial business. And that's the good thing about innovation in this world, because it's that place where real new things get seeded. That doesn't happen inside of big, large companies that make these things happen. So we're the feed for the rest of the world.
And that's it. I mean, you see that in every industry, right? I mean, look at the car industry. We're never going to have electric cars without Tesla. And you're never gonna, and then now you have Rimax and Rivian and Lucid and all of these emerging companies doing things that were never possible before, with new materials, with new technologies, rethinking the way the user experience can be. Instead of just doing the same copy and paste thing over and over. So I'm a car enthusiast as well, so it's a sort of easy analogy in my head, but I think we see it in a lot of industries where we're never going to see innovation come from the big incumbents.
And they're coming along. All the big incumbents are coming along, but they're behind the curve.
But we're pulling them kicking and screaming, right?
Yep, that's right.
Before I let you go, before we wrap up today, do you have any quick questions for me about anything we're doing or anything on that front?
Well, you and I just had a meeting this last week, so I'm actually pretty much up to speed with what you're doing, and we're really happy to be working with you on these things. Where do you see GlasCurtain being in 10 years from now? Is it going to be an Edmonton-based alone manufacturing facility, or you have bigger plans than that? What are your kind of long range plans?
Yeah, no, that's a great question. I mean, I think that like you guys in Sydney, there's a lot you can do with that one. It's sort of like what we're calling a hub and spoke model, right? Where we centralize the fabrication in Alberta and we decentralize the installation across North America, Northern Europe, beyond, right? So we like to work with local installers to bid the projects to the general contractors. We bid to the glazers, the installers. I think that in 10 years we will definitely have a much bigger footprint in the US market. I would love to have a couple of projects under our belts in Northern Europe as well. But I see us, continuing to evolve. We currently have, one pultrusion partner. It could be that we need to add a second pultrusion partner as that demand capacity grows. But yeah, I mean, our team, I just see us continuing to grow and expand on our current trajectory. We have 30 plus installation partners now. 10 years ago when we started, we had one, right? So, in 10 years from now, could we have 100 installation partners? I absolutely think so. A much bigger footprint, in places with those kinds of stretch codes like Massachusetts, New York, potentially Colorado. That's kind of what we see happening. Or organic growth, but healthy compounding, well into the double digits compounding, annually. Nice healthy growth.
Speaking of that, it seems to me that you're predominantly involved in vertical glazing. Is your product applicable to sloped installations as well? Are there any limitations on that?
There are absolute limitations to that application. So this is really designed, Thermoframe is really designed to be a true curtain wall system. So there is possibility for some deviation from that. We've done designs, up to 5 or 6 degrees of slope. But doing something like a 45 degree slope, that's technically a skylight at that point. And skylights have different drainage requirements. And those different drainage requirements are different for every, size and every scope of every angle. And so those would require custom dies for fiberglass. And, unfortunately, again, at this point in the evolution of fiberglass pultrusion technology, we're at the point now where it's super strong, super durable, but the die costs are very high. And so we are limited really on the die cost to do a skylight for one room or one project even. The die cost will be at least 10 times more than aluminum would be. But yeah, at this point, the thermal performance and just the engineering of fiberglass really wants it to be vertical or very close to it.
Just that was a curiosity on my part. Good.
I mean, aluminum has its places, in the facade systems that we do. So doors will typically be aluminum, pretty much always. But we'll do the curtain wall framing in fiberglass, and we'll do the operable vent framing in fiberglass. So any operable vents that are, again, vertical, operable windows, those will be fiberglass framed in our systems as well. But yeah, aluminum still has its advantages. We just definitely try to minimize it as much as we can for obviously the thermal performance and operational benefits.
And embodied benefits.
And embodied benefits. Absolutely. Thank you.
There you go. Now, you couldn't forget that one.
No, you teed that one up for me. So thank you very much again, James. Where can people find you online?
They can find us on any of the normal social media platforms. We're on all of them. Our website is www.advancedglazingsplural.com. And we're happy to talk to anybody about anything, even objections. Please talk to us.
Wonderful. Well, thank you very much, James, for joining us today on Curtain Wall Conversations, episode 8. It's been an absolute pleasure, and we look forward to working with you more in the future.
Good. Yep. Thanks, Peter. Good to have time with you. Take care.